Okay, first, I guess, sort of kind of reminder, I guess. Um, the For those of you who end up in waiting rooms, whether it's my class or even other classes, if you sign into Zoom using your cuw.edu, you'll automatically bypass the waiting room. It'll let you into the room. Then you're like validated. So only if you come in as like a guest or under like a Gmail account or something like that, do you end up in a waiting room. And just so you know, it's sometimes hard for the teachers to see, unless you're staring at this version of the screen. But once you start sharing your screen, it becomes a little bit less obvious that there's somebody in the waiting room. So like right now, I can see that he's in the waiting room, so I could admit him. But otherwise, it's not very obvious once the class starts. So they would have to text one of their classmates or post on Slack and have one of you see it, because I'm probably not going to see it in Slack during class. To relay to me, I have to let somebody in. So I would encourage you to log into Zoom using your cuw.edu so you don't get locked out of a class. Got it? All right. I did add a couple of, even though we're not full again today, but I did add a couple of more seats of capacity in the back of the room. So I added 3.5 seats. So for if anybody showed up last time and got turned away because the class was too full, the half seat means you have to have a laptop on your lap, but it's a nice cushy kind of couchy looking like good seat. So you can decide if that's a good trade-off for you or not. But today we have 3 extra normal capacity seats anyways. But again, everybody is allowed and encouraged to come to class in person. That's why I asked if you have a strong opinion. I got you on the list, but if you don't care, being online is fine. I don't mind. But if you do care and you feel like you can't come to class because we have capacity, let me know and we will figure out a solution, because everybody is entitled to face-to-face if they would like it. Okay. What was the last slide we did last time? Anybody know? Have we done the primitive types for Java yet? Oh, I think I gave you kind of a crash course in Eclipse last time for asking questions, repetition, and memory. That sound right? I think we had like a single Eclipse screen that had all that on it, and then I put it on to Slack. Yeah, so here's defining a variable. Here's our syntax for if-elses. Here's our syntax for a while loop and for a for loop. And I gave you kind of a equivalent in Python code here. Printing stuff out to the screen. We wrote a function here. Right now, we're just saying we're going to keep static in front of everything until we have an opportunity to talk about static. But our functions have a name. They have a parameter list, just like we did in Python, except our parameters have types, and they also have a return type. Go ahead. Slide 12, okay. Okay, yeah, so once we got down to the environment, that's where I jumped over there. We just kind of started going with Eclipse. So let me just kind of flip through this real quick and see if I haven't covered something. We basically took this slide and exploded it out into the Java equivalent of what we already know from Python. So memory, asking questions, and repetition. The mapping. We reminded ourselves programming is hard because human beings are really good at solving problems and we have trouble articulating that. And that's going to be something that you continue to get better and better with through this class, as well as the next programming class, CSC250. You know, we switch up the languages to further convince you that the programming language is not the important part. Computer programming as a skill set is the important thing that we're learning here. The language doesn't matter. Last semester, you started off, Python was hard, then you got your comfort zone with Python, and now you're out of your comfort zone because you're in Java, and it's asking you for return types and things like that, but you'll get into your comfort zone with Java, and very quickly you'll see that it's the same kind of mentality, the programming mentality that you're actually going to be focusing on in here, not the fact that the language is Java. Okay. Talking about the right tool for the job, you start putting yourselves into industry type situations, and you know, a boss or somebody gives you a project and you have to sit back for a second and say, okay, well, how am I going to solve this problem? I kind of recall, I think we talked about this a little bit, you know, but the idea being you don't always want to default to whatever programming language or technology you're most comfortable with. Now that plays into it, right? You know, maybe you say, well, can this be accomplished with my kind of my go-to tool? If you're a .NET developer or a Java developer or a web developer, and you have your set of tools that you typically operate off of, maybe those are your go-tos. But you should at least go through the question of, is that an appropriate tool for solving this problem? If not, let's look at what the appropriate tools are, maybe figure out what's closest to what I've done, something like that. So maybe the transition period isn't too much, but again, relying on this idea that computer programming is the skill set, not the language. Any of us can get up to speed in another language very quickly. Okay, you know, and you know, even take from last class to this class, you know, some of you played around with Eclipse and started, you know, and part of that was just learning curve of getting Eclipse up and running, making sure it recognized your Java virtual machine and some things like that. So getting your development environment going maybe takes a little bit of work, and there's some learning that occurs in that process. But once you have it up and running, it just kind of works, right? You know, it seems just like your Python environment before. You sit down, you write some code, you hit a play button, and it runs, or it doesn't run, and it screams at you, whatever it is. But you know, there's some transition stuff when you start using a new technology. But we're not talking about like months of relearning how to program in this new language. You know, we saw last class, and in a single class period, we basically did the conversion between Python and we probably did what, 85% of the conversion. We're going to run into some other weird things as we go along, but we hit the highlights of memory, asking questions, and repetition.
I have a question.
Go ahead.
So if all programming languages can like do the same thing, then like why would one of them be like better for a certain problem than another?
Well, because they're all built around the same core concept of telling a computer what to do. But certain languages were kind of initially conceived to maybe solve a particular problem. So they were built on top of, you know, almost always an existing programming language that was general purpose. So like if you think back to last semester, we had our chart that, you know, showed C and C++ and Java and kind of where they all fit into the world. But, you know, like when PHP came out, PHP is a Java or is a C-based programming language, but it was specifically trying to make lives easier for web developers. So it has some shortcut tools built into it that makes things that happen very often in web programming, you know, like one line of code instead of 8 lines of code, that kind of stuff. So sometimes they'll lend themselves to solving certain problems. That isn't to say you couldn't use another tool to solve those problems, but that's what I mean by right tool for the job. But the core functionality of them is the same. It's more just the bells and whistles. I think a good example might be like I got over the summer, I got new smart TVs at my house. I used to have Samsung, and now we have LG TVs. And the remote, the TV remote, you know, if I handed any of you a TV remote, you would pretty much know how to use it, right? TV remote's like a programming language. But this particular remote has hot buttons for Netflix and Amazon Prime, and I think maybe one other one. It's a programmable one. So it just happens to be very convenient for launching Netflix or launching Amazon Prime if you do a lot of streaming with those two services. So that's kind of an example of what I'm talking about. Okay. You know, we remember programming is like a sport. We got to keep putting in our reps. Some of us came out from last semester and feel like, you know, maybe hopefully all of you feel like you're better than you were at the beginning of last semester. Okay. So hopefully all of you feel like you're better than you were at last semester, but many of you, probably most of you, still kind of feel like you're not very good. And that's okay. You're still putting in those reps. Okay. And in this class, you're going to come out of here, and hopefully by the end of this class, you will be better than you were at the beginning of this class. And then you go into 300 and you'll still feel like you suck at certain things, but they won't be the same things, and they'll be much more complex things, and so on and so forth. Keep putting in the reps, and eventually programming just becomes this fun thing that you sit down and say, oh, I have an interesting problem to solve. The right tool for the job is to write software to do this. And it becomes something that you do by choice, not because it was assigned to you. All right, then again, the reminder, programming is a superpower. It'll be worth it, pay you a lot of money. Not to say that chasing the dollar is the end all to everything, but you know, if a lot of people can't write software, so writing software is a superpower that you can apply in a lot of different industries today. All right, and you know, we talked about this last semester, but because of what we're going to be really focusing in on this semester, we'll rehash the idea of an algorithm. Think of it like a recipe, right? So if you're going to make a lasagna, you have to follow, here's all the ingredients I need, and you got to follow those steps in order. You can't bake it before you've, you know, put the other things into the pan. So, and in this class, we're going to be looking at a lot of searching and sorting various well-known algorithms and looking at the difference between them and writing them, and then creating kind of hybrids of them. So this idea of having kind of a way of accomplishing something and using that as a baseline, and then changing it is something that's going to be very important to us. So this idea of an algorithm is a set of instructions that unambiguously solves the problem. All right, and then as a reminder from last semester, and I've also been mentioning it during the last several classes, one of the things we want to compartmentalize here is that, you know, this kind of goes back to this idea of using the right tool for the job, but also kind of knowing what kind of language you're working with in any particular point in time. So in this particular case, we look at our languages, we decide, okay, is this I think I give you yeah, so we have high level versus low level versus machine language. This goes back to, you know, how CPUs work. We all pretty much have settled on high level languages are where we want to be, right? You know, we want to write we want to write a minimal number of lines of code and accomplish the most that we can in those minimum lines of code. Looking at Hello World in Linux is interesting. That's low level version. We could accept that, but ultimately we don't want to tap things out with zeros and ones. All right, so we want to be high level languages. Compiled versus interpreted. This is something we talked about last week when we looked at compiling our Java program versus interpreting our Python program. From a human being's perspective, it was the same, right? In fact, we might have even said that Java seemed more inconvenient because we had to do two steps: compile it and then run it. Make sense? But the reality is that once you get into the actual tools that we use for programming, you would say that with Eclipse, we just hit the play button and it runs. Just like with Python, we just hit the play button and it runs. Okay, but those are giving us conveniences for what we saw under the hood, what's actually happening. In Java, it's compiling it and then running it. Python, it just runs it because Python's an interpreted language. Java is a compiled language. So before we run it, it has to be translated into low level and machine code, and then we execute it. Make sense? All right, so we have compiled versus interpreted. Now, only under very specific circumstances is that decision going to play a major role in the in whether something's the appropriate tool for a job. Only when they need to be really fast, when speed is super important, because most of the time our computers are fast enough, we're not going to notice the difference. We write any program that we're going to write in this class and we run it in Java and we run it in Python, it's going to feel fast. Both of them are going to feel fast. Loosely typed versus strongly typed. This kind of just goes hand in hand with our compiled versus interpreted. I personally like strongly typed languages. I feel like having a more structured language that forces you into, well, that doesn't allow you to make kind of loosey-goosey decisions is better. But a reality around this is we don't really necessarily have to have that preference, because it kind of goes hand in hand with compiled versus interpreted. If I'm using a compiled language like C, C++, Java, C#, Objective-C, Swift, it's going to be a strongly typed language. They all are. Compiled languages are strongly typed. It's just the way that they're put together. Interpreted languages run on top of an interpreter that was written in a strongly typed language, a compiled language. And interpreted languages typically will be loosely typed. Just the nature of those languages. One's not necessarily better or worse than the other. I just think certainly from a programming competence and programming education perspective, I think I've mentioned it before with Python. Something I like the most about Python is it forces indentation. Historically, when I've taught programming, before Python was really a popular thing or even a thing, I was, something that students struggled with was writing code that was properly indented. And then they'd come and ask for help, and everything is like left justified, or 4 or 5 things are on the same line. And, a lot of it was they couldn't even read their own code. So that was kind of an ongoing weakness of beginning programming students, is they didn't set as a priority formatting their code into something that was relatively readable, debuggable, things like that. So something I really like about Python is that it forces indentation. I think it's its greatest superpower, to be honest. But if I had my druthers for teaching a first programming class, I would pick a strongly typed language so that it forces you to go through that process of saying, I'm about to create a bucket of memory. I want to remember something. I'm going to create a variable. What kind of value am I going to be holding inside this variable? I like that idea of forcing that programmer to go through those 2 or 3 steps of deciding, what am I trying to accomplish with this line of code? Where Python says, oh, you can just create a variable. You can hold a number in it now, you can hold a string in it 3 lines from now. Now, something you probably recognize from last semester is I would rarely use the same variable to hold multiple types. You just create a new variable for that. And you try to name your variables something that's very descriptive of the kind of value it's going to hold. My name, something like that, or first name, last name. But the idea is that from an education perspective, if I had my druthers, all the languages would be strongly typed and all the languages would force indentation. Python's very nice in that it does force indentation, and none of the compiled languages do. They all operate off those curly braces. They'll let you put the whole program on one line if you want. And beginning programmers will tend to do that. So put a lot of emphasis on your indenting. It'll make your life easier when you're debugging. So that's just kind of a look behind the curtain, if you will, for strengths and weaknesses of languages from a teaching perspective. I would rather you have gotten good practice last semester with indenting than the strongly typed side of things, which is why we use Python in the first class. All right, but these 2 bullet points go hand in hand. Compiled versus interpreted, loosely typed versus strongly typed, same thing. General purpose versus domain specific. Domain specific is not going to become part of your lives really until much later, and maybe as seniors, if you do something with an embedded system like an Arduino or something like that. Or if you end up getting your degree and you go out and work in industry somewhere and you start writing software for dishwashers or furnaces, things like that, that have very specific, a furnace is a computer. It has a computer in it, right? But it's not a general purpose computer. You're not going to play the latest version of, Call of Duty or something like that on your furnace, right? The furnace is going to have a very specific set of things it knows how to do. And if you're writing software for that furnace, you would be using a language probably based on top of C, so it would look familiar to you, but it's going to be a language that's going to have a significantly reduced number of magic tricks that do furnace stuff, if that makes sense. So when I say domain-specific language, I'm really talking about that type of thing. Mini languages that are built for solving a very specific task. When you're learning the program, all of our languages are general purpose. They're like, hey, here's a programming language. It can solve anything that programming languages can solve. Getting back to the question from a little bit ago, certain languages lend themselves to certain problems more so than other languages do. PHP is much more of a web-focused language than C, for example, okay? Object-oriented versus procedural. In many ways, this is taken out of our hands now as modern developers because all of our modern languages are object-oriented. It's the current way of thinking about programming, because one of the jobs that a programming language does is it tries to give us a tool. I mean, the first job a programming language does is it says, we have a tool that can tell a computer what to do. But secondarily, we might say that a programming language also tries to allow the human being to solve problems in the way that we're already used to solving them, right? And in real life, we work with objects. We got a sign on the door there, put your mask on, right? This is a mask object. It has features. It has the little ear hooky things and stuff like that. So, we think about the object that is a mask. And even though building this thing required, I guess, sewing machines and stuff like that, that's not part of this object that we interact with. We interact with the little rubber bandy things, right? We use it through those public interfaces to put it on. The fact that somebody spent time and effort sewing it and things like that, those are nice things. It wouldn't exist without it, but it's not important to us in terms of using it. If we were implementing the mask, that would be important to us. Using the mask, less important to us. We just need access to those, the public things. You remember from last semester, we had the object-oriented versus the procedural version of the telephone, where the telephone was a big pile of wires. If this was this mask was the procedural version of the mask, we'd see all the thread laying out there, but we'd find the little rubber bandy things and all that, and like, oh, okay, well, that's a mask if I just kind of bunch it up pretty good, something like that. But the way human beings solve problems in real life is in terms of objects. We accidentally do it. We don't think about them in terms of objects, but it's always, oh, I'm gonna grab my phone. That's an object that has, when you say phone, it has implications, right? Especially today, if somebody says they're gonna grab their phone, what is it? 98 out of 100 times it's a smartphone of some kind. There's an implication that they get text messages. They can probably check their email. They can run apps, things like that. Not every phone can do that, but that's kind of the implication when somebody says phone now. That's the kind of object they're referring to. Make some sense? We already solve problems in our real lives in terms of objects. And these programming languages, the modern programming languages we use, since their purpose is for us to tell a computer what to do using the way we already solve problems, they tend to be object-oriented. Python had object-orientedness added to it as a secondary, not a secondary thought, but it was kind of a bolt-on to it. So we saw that the way it accomplished all object-orientedness was a little bit funky. And you're going to see that once we get further into Java, where with Python, we had to pass around that variable called self. Remember that guy? In Java, the equivalent of self is going to be something called this. And we're going to see plenty of examples of that, so don't worry about that right now. But that just kind of is magically there. That's not something we pass around all over the place. It just is. Okay? All right. And we all remember from last semester with how CPUs work, collection of magic tricks. You know, you probably at some point I had you, you know, I wiggled my thumb like this, and I said, "Oh, how many of you can do that?" And everybody could do it, right? And I did this. How many of you can do that? Well, neither of those things are impressive in and of themselves, but I could put those two moves together and pick up my water bottle, right? I accomplished a task using two tiny little magic tricks that aren't impressive in and of themselves. Computers work the same way. Our CPU gives us a whole bunch of these little individual magic tricks that if we string them together in the right order, we can accomplish real things. And high-level, general-purpose, object-oriented programming languages that allow us to solve problems in a very similar way to how we already solve them allow us to ultimately tell a computer how to string together a zillion magic tricks to accomplish real things. Okay, but there's a lot of power tools sitting between us and the machine language behind the scenes because we don't want to have to write the zeros and ones. We don't even want to have to reference the individual magic tricks. We want a power tool where we can write things that make a lot more sense to us and then have 2 or 3 layers of things between us, compilers or something called a linker, which we'll talk about in the 450 systems programming class, but things that ultimately take our high-level code and make it into something that will run on that computer CPU. All right, so we've already talked about this, but just to reiterate, where does Java fit? It's high level, it's strongly typed, it's compiled, it's object-oriented, and it's general purpose. And it's popular. If you go and look online for, you know, if you were graduating next month and you looked online, you were shopping for a job with a computer science major, you're going to find a whole lot of jobs in Java, a whole lot of jobs in C#.net. You'll find plenty of jobs in Python, specifically in the world of data science and machine learning. AI stuff uses a lot of Python tools for that. If any of you are in the any of you taking the machine learning class this semester? That's this semester, isn't it? I think so. But in any case, that class uses Python because a lot of the tools for doing artificial intelligence, machine learning stuff, those libraries are written in Python. So that language, even though the Python language is a popular enough language, but a lot of the places that are looking for you to come in with that competency aren't really asking you to be general purpose Python programmers. They want you to leverage your knowledge of the Python programming language to use third-party tools for creating neural networks and training what are called classifiers for making machine learning type decisions, object-oriented type decisions. If you remember one of our tech speakers last year, that Eric Johnson from Aurora WDC, his whole business was built around this idea of using machine learning and applying it to business analytics and decision making. All right, so let's talk about primitive types in Java. So first of all, what is a primitive type? Primitive types are, so first of all, right now we're now starting to focus on this idea of types because Java is a strongly typed language. So when we create a variable, we have to put something in front of that variable and say, this is the kind of value that this variable was built to hold, right? In Python, go ahead. I heard somebody squeak or something. Is there a question online? Yay, nay, no? No. All right. So in any case, we have to know what to put before that variable. And what I mean by that, if I come back over to our example last time, when I defined a variable right here, in Python, that would have been enough, a = 0. And I'm kind of implying that I'm going to hold a number, right? But in Java, I have to put something in front of it. I have to say, this is what type of value this is going to hold. We have to know what is that list of options I can put there. What are the things that are built into the language? And then what are things that I can invent myself through objects, all right? Now, the simplest things that are built into the language are called primitive types, all right? And I'll just quickly, just in our slides here, I'll just throw well, in the code here, I'll say primitive types. And these are byte, short, int, long, char, float, double, Boolean. So those are our primitive types built into the Java programming language. You will also find that the same primitive types built into C and C++. Actually, technically, C uses an int for Booleans. C++ uses a macro for Booleans. C# doesn't like to write as much. They call it a bool. I think you're getting the point. Trues and falses exist in as part of the types in all these languages, but in Java it's spelled out as Boolean. All right, so these are the primitive types. So let's call these the simple types that are built into the language, and all they can do is hold a value. So all these types can do is hold a value. They can't do extra special stuff, which we saw in Python, like lists could tell us different things. You know, lists could give us one of their elements at bucket 3, for example. You know, so we had some types in Python that could do some extra things other than just hold a value. Or with our objects, they could hold more than one value. All right. But primitive types are our simplest kind of types that are, you know, let's call it our bread and butter of writing just normal logical programs. So why do we have all these types? So let's look at these first 4 here. Byte, short, int, long. And I probably mentioned this last, did we talk about the Y2K bug last semester? That sound familiar to you? Okay, so we'll go through it pretty quickly then. So byte, short, int, long, these guys are all built for holding positive and negative whole numbers. So we would call them signed whole integers. Signed means it can hold positive and negative. So a byte can hold the numbers between -128 and +127 because a byte is 8 bits, 8 zeros and ones. So if I have, what's up? Not if it's signed. If it's unsigned, it's 0 to 255 because there's 256 unique representations of 8 zeros and ones. But if I have to hold positive and negative numbers, you take the absolute value of both these and add them together, you'll get 256. All right, well, you'll get 255 because a 0 is one of our representations. So a signed number can hold positive and negative values. And if I'm using 8 bits to hold signed numbers, what will end up happening is I have 256 unique signed numbers that I can represent using 8 bits. Okay? You'll learn in the 325 class next semester, which is computer organization and architecture, the idea behind how this is done. This is done through something called 2's complement. The way we encode a binary number to hold a negative value, done through something called 2's complement. So don't worry about that right now. Just know that the 8-bit number is somehow encoded so it can hold both positive and negative values. Okay? But the point is for us, if it's an 8-bit signed integer, the smallest number it can hold is -128. The biggest is +127. If it's a short, -32,768 to +32,767. So a wider range of values, but still not a huge range of values. If it's a int, -2.1 billion to +2.1 billion. If it's a long, think of this as -9.2 quintillion. I think that's what that comes out to. Big number. Well, actually, super small number up to a really big number is the range. But the important thing for us here is all 4 of these are built for holding whole numbers that are signed, positive and negative. So the question I would have posed last semester, because I think we covered a very similar slide last semester because we weren't at this time talking about Python specifically, we were talking about the history of programming languages. I would have asked, well, why do we need so many different types, all who are capable of holding positive and negative whole numbers? Anybody remember the punchline? So even though you vaguely remember the Y2K thing, you'd in one ear out the other at some point. Okay, so we'll cover it again. That's fine.
I mean, isn't it back to when like machines didn't have like memory was expensive and stuff like that? That's the whole thing.
Yep, absolutely. So, memory used to be really, really, really expensive in computers. I probably used the example in class last semester of a computer I had way back when that I had 8 megabytes of memory in, and I doubled the memory, and I asked, how much was an 8 megabyte chip? 8 megabytes, not, today your machines have 4, 8, 16 gigabytes of RAM in them, right? This computer has 64 gigabytes of RAM in it. Ridiculous amount of RAM, because RAM is now cheap, relatively speaking, right? Even if you buy RAM stock from Apple, it's still cheap relative to the history of it. Apple charges a lot for their RAM relative to what you could like order off of Amazon, but since everything's soldered inside the machine, you don't have the option to add RAM aftermarket anymore. Super smart by Apple, actually, from a business perspective. Super inconvenient from a consumer perspective. But in any case, that 8 megabyte chip cost me $1,000. I think we did the math. It was something like $128 per megabyte, something like that. And then we also did the math on like what the modern price per megabyte is, and it was something like less than a penny per megabyte using modern math. So memory used to be, and I also said this was back in I think 1994-ish, 1994 probably is when I bought that chip for $1,000. And I think that predates you, at least most of you. When were our birthdays in here? 2000? Okay, yeah, so predates you. But memory had already come down in price, is the punchline. So even though we look at that and say, well, $1,000 for 8 megabytes of RAM, that's ridiculous. I can't, my toaster has more than 8 megabytes of RAM, and that's probably a truth for some of your toasters, right? That's unfortunate, but it is true. I have a toaster that does Yoda toast, and it has way more than 8 megabytes. I upgraded it to 16 gigs just because. Because who doesn't need Yoda toast? The answer is nobody. Everybody needs Yoda toast. So punchline there is RAM had already come down in price when I paid $1,000 for 8 megabytes of memory. It used to be way more expensive than that. So, back to the rationale, because remember, these primitive types came from the C programming language, that came out in the late 1960s, which was before me. Okay, so those things had those computers had very, very, very little memory on them, like 32 kilobytes of memory on an expensive computer. You had to be careful how you used that memory. It could only fit so much stuff. So when you chose your types to use, you made sure you picked a type that was going to allow you to solve the problem you were trying to solve, but was also going to not use up all the computer's memory. But that also gives us the kind of the rationale for why the problems we solve with computers today are so much more complex than the problems we solved with computers back then. Right? I mean, if you only had 32 kilobytes of memory in your computer back then, Call of Duty or your favorite Nintendo game, whatever it is, that's not in the cards. All right, you don't have enough memory to do things like that. You didn't have enough graphics power to do things like that. So now our computing stuff has gotten so powerful that we can start thinking about some of those things. Excuse me. We can start thinking about some of those things, but we've almost ran out of problems to try to solve with modern technology now, and that's where we get into the machine learning stuff, where we try to create classifiers for solving problems that we have trouble solving ourselves by writing software ourselves. And I think was last class I talked about the neural network that I originally wrote, that in like my first exposure to a neural network that did the 1 through 5's multiplication table. I talked about that here, right? And then the 6 through 10s, I trained it on the 1 through 5's, then gave it something it had never seen before, and it got it all right. And you're just like, I've invented Frankenstein. It was a pretty exciting moment for a geek. But you know, now we're starting to look for new ways of solving problems that as human beings, we just can't articulate to the computer. We can't explain multiplication. We can kind of say how we do it, but we can't explain why it works. It just is, something like that. So that's where we start getting into neural networks for kind of representing some of those things. So we have 4 different ways here of holding whole sign numbers, because we used to have to be careful about that. Today, we pretty much always use int. And if int isn't big enough, we'll use a long. So if you need to hold a whole sign number in Java, call it 98% of the time, you'll just say it's an int. Even if you know it's only going to hold the number 1 through 10, which will fit inside of a byte, you'll put it in an int. That's just normal modern naming convention. You will pretty much never see somebody, a modern programmer, use a short. Okay, so you've never seen use a 16-bit signed integer. You will sometimes see bytes, but not for the reason of data size. You'll see it because a lot of streaming video stuff comes in streamed 1 byte at a time. So that's kind of like their correct size data type. So we happen to have something that fits bytes nicely. But not because we care about the size. All right, so for us, if you need to hold a number between negative 2 billion and positive 2 billion, throw it in an int. If it's got to be bigger than that, throw it in a long. If it's got to be bigger than what fits in the long, now we got to jump over to the object-oriented side of things and look at something like a big integer or a big decimal, which are built-in object types, but they're not our primitive types. So we're not focusing on them right now. All right, so this is our bread and butter for signed whole integers as a Java developer, as a C# developer, as a C++ developer, yada, yada, yada. All right, chars, these are 16-bit unsigned integers. These actually used to be 8-bit unsigned integers in the C years. Anybody remember why chars are, first of all, unsigned and why they're 16 bits? So a 16-bit unsigned value can hold 65,536 unique values. So that's 0 to 65,535. Why do we need to store 65,536 unique values in the a character primitive type? What's that guy representing? Well, what's a character?
Is it like one individual like keystroke?
Okay, so yeah, it's like it's a characters like our alphabet, or punctuation, or commas, or smiley faces are in there. So a single character, a single representation of the vocabulary or the alphabet of a language. And it started off way back when, because well, I guess I wonder who was the guiding force between it, but we used to use a character set called ASCII, American Standard Code for Information Interchange. And it just so happened they thought that the only symbols that were important were the symbols from the English alphabet, upper and lower case, the digits, things like that. So they only needed 8 bits. Actually, ASCII was technically 7 bits, but you know, the smallest representation we had was a byte. So we only needed 8 bits to hold all those, 256 unique characters. But then all of a sudden, through great ingenuity, we discovered there are other languages in the world. Now, how many of you didn't know that? Everybody. I should have asked the other way. How many of you knew that? Yeah. Well, it came to our attention very late, apparently. But again, in our defense, memory used to be really expensive. So we had to choose one of the languages, right? So we went with English. But in any case, now we use something called Unicode, right? Unicode can hold 65,536 unique characters, and it doesn't represent every single language on the planet, because you have some fairly obscure languages, and you're looking at the Congo and stuff like that. But you know, it does a much better job of representing the languages of the world. So it has this ultimately comes back to, remember, we are telling a computer what to do. Computers like numbers. We don't want to have to remember that an exclamation point is some crazy 16-bit value. We write exclamation point, the Unicode character set maps that to whatever the 16-bit unique representation for a, exclamation point? What an exclamation point is. Similarly, we look at, you know, some of the Chinese Han characters, things like that. Same thing. You know, there's a mapping for that. So chars are 16-bit unsigned. Why are they unsigned and not signed? Well, we don't need a negative number. The Unicode character set starts at 0 and goes up to 65,535. Storing a -8 is not going to help us because that's not on that chart. So it only needs to be unsigned. Make sense? So chars are actually stored as numeric types. But when we use a char in our programming language, whether it's Python or whether it's Java, because the type is char. Types do exist in Python, just the programmer isn't required to designate a variable for holding a certain type. If you put the char A inside of a variable in Python, Python will treat that guy like a character, right? And if you go and you print that character out, Python's not going to print the number associated with it, the Unicode number. It's going to print out the character that a human being expects to see. You have to force it to show you the Unicode character. All right, so that's why chars are numeric, because computers like numbers, but that's why they hold 16-bit values, because the Unicode character set dictates that. Okay, floats and doubles. Float is kind of like the integer version of floating point numbers, like 3.14, that kind of stuff. Whereas longs are kind of like doubles are kind of like the long version of floating point numbers. They can hold more significant digits, larger values, before and after the decimal point. Normal convention says that if you're going to use decimal point stuff in modern programming languages, you use doubles. So if I'm defining a value to hold the value of pi in Java, I would say double pi is equal to 3.14159, whatever. Take it as far as you want. That's as far as I know. Even though this would fit inside of a float. But notice this guy over here, it's upset that I've put it in float because it's saying this is a double type. Type mismatch, cannot convert from a double to a float. So if I really want to force the issue, I can tell Java, trust me, that's a float. But what we just saw here by definition is modern languages have agreed with this convention that, oh, if it looks like a decimal point number, it's a double. We're going to treat this guy. So this is a decimal literal, right? A decimal point value literal. Those kind of values are of type double. We do see the use of floats certainly in C and C++ programs. We also see it quite a bit in game programming because a lot of times when we're representing like XYZ coordinates, things like that, or things with rotations, they're done with floats because it does use less memory. Because a lot of times when you're dealing with video games, you're trying to maximize the performance of a graphics card. And graphics cards, they're kind of like, their superpower is working with floating point numbers, specifically floating point, not doubles. So we don't give them more precision than they need because it's not useful to them. So we might as well reclaim that memory and use it for something else. So we do still see floats every now and then, but generally speaking, from a generalistic programmer, your go-to move is to use doubles if you have a floating point kind of value. And then Booleans, true and false. We use them all over the place. We use them in our conditionals when we're asking questions. We use them in our loops when we have our Boolean expressions. So these are our primitive types that are built into the language. So out of these, you will commonly use int, char, double. You'll commonly work with Boolean expressions, but you probably won't necessarily commonly create variables of type Boolean. Not that you'll never do it, but it's just not common. If you were going to look at this slide and say which of these are the most common types I'm going to put before my variables, it would be int, char, and double. That's the popularity contest. Probably in that order. All right, questions about primitive types. Significantly more important to us this semester because we are now forced to put types in front of our variables. Again, we reviewed some of the explanation behind it, but these aren't the only types built into Java. A statement I maybe already said, but I'll say it again, is Java is what's called a string-based language. And do you see string represented here anywhere? Strings in Java are something called objects, which we've been introduced to before in Python, but in Python we wrote our own objects. Here we get a whole big collection of objects that come with Java that allows us to solve some problems, and one of those is the string class. All right, and you can look through these signs here. You would think that when you have you're like sharing your screen and stuff, like you think Outlook wouldn't like pop up your like appointments. That's kind of a weird thing, right? I don't think I have any inappropriate ones, but that would be still a, yeah, I don't know. Yeah. Huh? I haven't seen any, no, because I get a beep or something like that from Slack, but I don't get the message popped up here. So it seems to squelch that. But I specifically use Outlook for my calendar on here. I don't use it for my email. The Mac calendar doesn't seem to mesh with my Outlook calendar as well as it should. It used to, but whatever. So Outlook's not doing its job, but it's fine. So if you want to read more into this, I give you some math examples of more than way of holding integers in here, and then different ways of representing chars with ASCII versus Unicode. So I have the text base of what we just kind of talked about. All right, so we've already seen some examples, some coding examples of dealing with variables. So type, variable name equals the value followed by a semicolon. Already seen it. All right, so let's look at strings. So the first thing I'm going to bring up here is Java string class. I'll just search for it here real quick. So here is the documentation, and as we get farther into the class, we will get very good at reading the documentation, but I'm just going to do this as a first level thing. So these are strings in Java, and strings know how to do a whole bunch of stuff. We have this thing called the method summary, and we're going to look at several of these methods related to strings today. Okay, these are things that strings know how to do. All right, so I'll refer back to this here in a few minutes. For right now, let me just gut all this stuff so I have a clean slate. All right, we'll create a string s is equal to hello. We'll create a string s2 is equal to elephant. All right, so I gave myself two variables, one named s and one named s2, both of type string. Notice that objects typically start with a capital letter. It is not a rule. I can certainly, when I create my own objects, I can certainly have them start with a lowercase letter. But if you just want to see the evidence here, if I come here to the documentation and I go to frames, In the Java, this is actually an older version of a language, but it's fine. It'll get my point across. Here's all the classes that are built into the Java language over here. You notice how all of them have capital letters in front of them? I'll zip way down the line here. Still all capital letters. Naming convention, popular naming convention is that classes start with capital letters. Got it? But it's not a rule. You can write your own class that isn't, but pretty good chance that classes start with capital letters. And of course, if I was writing this in C#, this would actually work because they have a, what do they call it in C#? A macro for it. But in C#, the string is actually lowercase, which maybe, I was going to say, which maybe is more appropriate, but the reality is that all of the primitive types that we just looked at, the int, the chars, all those guys can only hold a value, and that's a true statement. And all of those start with lowercase letters. Our object types can potentially hold 0 or more values and also potentially do other things. So they're special. And the naming conventions we just saw, they typically start with uppercase letters. Now, with that in mind, since strings can hold a value and then also do other things, they are objects and therefore should be capitalized. But in Java, as well as C#, strings act in many, many situations like primitives. So you could make an argument that they should start with a lowercase letter. But in any case, Java has strings starting with an uppercase letter, but they do behave like primitives. I'm going to prove that to you here in a little bit. Okay? But in any case, let's just introduce a couple of our popular methods in here. So first of all, I'm going to do a system.out.println. Remember in Python, we can do something like s at bucket 1, and that would give us this e. Remember that guy? In Java, we say s.charat1. Give me the character that lives at index 1 in the calling string. So this is a method that is part of the string class. So I come over here, I go down to the method summary. Right here we have the charat method. It takes an integer as a parameter and it returns the char value at that specified index. And it returns a char. That's what he gives me. All right, so that will give me a char from S. If I want to get a char from S2, let's see, 0, 1, 2, 3, 4. Let's ask for bucket 4, which is the H. So this should give me the E and then the H. I'll go ahead and hit play. And there's my E and my H. Okay. So that's kind of our mapping. So S2 at bucket 4. There's still 0-based index, just like Python was, so on and so forth. I also have a method called length, which will report the length of a string, as opposed to lang of S, lang of S2. I use the length method from the string class to return the length. This guy is a method, but he takes no parameters. But since he's a method, he does have an open close parenthesis here. this returns the length of the calling string. In this case, the calling string is S. This guy returns the length of the calling string, which is S2. So she gave me a 5 and an 8. 5 and an 8. So far, so good. All right. Let's see. In Python, we had a, was it find? Find S L. Find S2. Let's do N. We have something called index of. Okay, so the index of method, it will return the position in S where this character is first found, or a -1 if it was not found. Remember that logic? If it finds it, it'll tell you the first place it found it. Otherwise, it'll give you a -1 if the thing it's looking for is not there. All right, so for an L, I'll give us one more. I'll put a Q. So there is no Q in S, so we should get a -1 on this guy. So there we found a L at bucket 2. That's our L, the first L it found there. That's bucket 0, bucket 1, bucket 2. So return the position of the first L, not the second one. Then for an N, it found an N at bucket 6 in elephant. And it found a Q. It did not find a Q in S. So it gave us a -1. What time is this class out? 50? 55? Which is it? I think it is 50. Can anybody corroborate? I don't want to keep you long.
Yeah, we get out 50.
50. Got it. All right. 2 to 1. All right. So we got 9 minutes, 8 minutes. So we're still good. Let me get through everything. Okay. So this makes sense? So just like I kind of showed you with the primitive types, these are very popular methods you'll be working with strings. But in no way does it represent all the string methods. You see here we have a whole bunch of string methods. I'm still scrolling. So a whole bunch of stuff that's in there that can do other things. All right, but I do want to show you an example now how in Java we treat strings like primitive types. So I'm going to go ahead and create a third variable up here. We'll say string s3 is equal to hello. All right, so first I'll go ahead and I'll say system.out.println s equal hello. what should that print out? S is hello, S equal hello. Should that give me a true? This is the Boolean equivalence operator, just like it was in Python. So S is hello, so this gives me a true. Similarly, S3 is equal to hello. That also gives me a true. Similarly, S equal to S3 should also give me a true. Now this is very misleading though. And let me show you why. I mentioned that in Java, strings act like primitives. I'm going to create a fourth string, but I'm going to use the full constructor for making this string. Remember in Python, we use constructors whenever we created objects. So I'm using a constructor to create an object whose value is hello. So now I'm going to say S equal to S4. What do we expect the answer to be? Hello is equal to hello. We would expect it to be true, but it's not. It's false. This guy right here returns true because it is comparing the contents. Well, actually, it's comparing the value of S and S3. The value is a pointer to a place in memory. So what happens is when we first use the string literal hello in our program, Java creates a new value in memory in string literal space for hello. Let's just call it memory address 100. The second time I use that string literal, Java says, oh, well, I'm not going to waste any memory. I'll just make S3 point to the same place S points to because I already have the string literal hello in memory. So S and S3 both, even though we've written it as they both contain the same value, the reality is they both equal the same memory address, which points to the exact same value. Not two values that look the same. They are the same value. When I created S4 here, though, I used the constructor for it. I mentioned that strings kind of act like primitives in Java, and this is kind of an unfortunate reality of Java, I guess, is because we use strings so often. Earlier in the class, I mentioned that Java is a string-based language. Strings are really, really malleable in Java. Like, you can work with them easily, which is great. But it also means that Java included a special syntax that we have here for working with strings conveniently by creating them like we create primitives. Every other object in the Java language, so things that start with a capital letter, we would use this syntax for creating instances of that object. We would use the new keyword, which gets us some memory. So what I'm saying here is I'm saying bypass the normal rules. I want to create a new memory location to hold a string equal to hello. So S4 actually holds a different memory address than S and S3. S and S3 both point to the place in literal memory where the string literal hello is stored. Whereas S4 points to a brand new place in memory. I'll prove that. I'll create a string S5. So S4 is not equal to S5 either. This guy holds a memory location, which is different than this memory location, which is different than S and S3's memory location. All right, so S3 equal to hello. Both of these guys are equal to, because hello, this string literal will boil down to its memory location, which is in Java literal string space. S equal to S3, that's true. S equal to S4 is false, because they point to different places. S equal to S5 is false. And then the real kicker will be S4 equal to S5 is also false, because they're their own places in memory. That makes sense? Now, in our last minute, realistically, when we compare strings, we're not talking about their location in memory, right? We want to know, do these strings hold the same string of characters? So we use a method, s dot equals S4. There is a method called equals that will return true if the calling string contains the same characters sequence as the string you pass it. That will be true. There's our true. There's also a ignores case. So if I change S4 to have a capital H, this guy will return false, but this guy will return true, because I can make it not pay attention to case sensitivity as well. All right. So I'll just say, this is likely what you mean when you compare strings. Make sense? All right.
So basically, instead of checking for a memory address, you're checking for the same.
Basically what I'm saying, unless you absolutely know why you're doing it, don't use the double equal sign with strings or any other object. You're comparing memory addresses. Chances are, if you're comparing strings, you want to know what is inside those strings. Do they hold the same character sequence? Use the dot equals or the dot equals ignore case method to accomplish that. Make sense? All right, I'll post this code up on Slack. I'll upload the recording. I think we'll probably have our first real homework assignment on Thursday over the weekend. So I will see everybody on Thursday. All right, any questions from online before I start processing the recording?
I have a quick question.
Sure.
So I've been writing some functions in Java, and when you were writing yours and like talking about them, you didn't have to put public in yours except for main.
Yep.
It didn't work when I didn't have public.
You'd have to show me, you definitely have to have public in front of main. You don't have to have public in front of other methods as long as you're calling them from the same context. So if you send me the code where it's not working, I'll tell you why it's not working.
Okay, sounds good.
All right.
Thank you.
Anything else?
Nope.
I have one as well.
Sure, go ahead.
I remember back in Python there was a way that you could display the memory address of a variable. Is there a way to do that in Java? So you can
Yeah,
compare?
we'll see it. Well, there actually is not a convenient way to do it for strings, but you'll actually by default show memory addresses of objects in Java. You have to try not to. You'll see that when we get to it.
Okay.
It happens by default in Java is the punchline. That's what I'm saying. Just not with strings. Strings are like the special case in Java. Okay, I think we're good then. So let me get the recording processing and then we can look at your thing.